So to continue this energy balance, just flip through these again. Pi r squared times S and pi r squared times S times A, the energy that's received as short wave, outgoing long wave. We did this simple calculation and said we end up with an emission temperature of minus 18 degrees, which is clearly wrong because the Earth is not that cold. So what is happening? We need to add a little bit of more complication. If just look at it for a little bit and you will understand how simple it is, right? We didn't include any atmosphere in the previous calculation. We just said there is a surface which is intercepting the energy and it's heating up and it's sending long waves back. But it's not that simple, right? If the sun's energy is mostly reaching the surface and heating the atmosphere from below, an atmosphere is a greenhouse effect, that means the energy balance must include the atmosphere. And is it just one atmosphere? Of course not. It turns out that the atmosphere also is stratified, which means it has many layers, but we will again simplify this calculation. So now let's look at this energy balance again. We are now looking at a unit area instead of this global energy balance. Okay, that's a slight switch. Before we looked at how much energy was coming into the Earth's surface, how much was being sent back as long wave, how much was being reflected as short wave to do the balance. To do this, it's better to look at one unit area. So per unit area, again, you are receiving S over 4 because you are dividing that pi r squared S by 4 pi r squared because it's getting distributed on every point on Earth. Small change in the concept, just think through it, okay? And what is being reflected? S divided by 4 times A. So that's net energy that's reaching the surface is S divided by 4 times 1 minus A. What did we do here? We didn't include any absorption in the atmosphere, and we are assuming the atmosphere is just one layer. Again, simplification to just give you a sense of how the energy balance is done and also how complicated actually it is when you do it in a realistic multi-layered atmosphere with albedo changing everywhere and so on and so forth. Okay, so the energy that's receiving the surface is heating the surface and creating a surface temperature of Ts. Again, going to the black body radiation calculation, the energy coming from the surface in the long wave is simple, sigma times Ts to the 4th. What is happening to this long wave coming from the surface? Atmosphere now is not transparent to long wave. We assumed for simplicity that it's transparent to short wave, but for this simple calculation, we must include its ability to absorb long wave because that's the critical part of the greenhouse effect. So that energy sigma Ts to the 4th is being absorbed by the atmosphere. We are assuming that it's completely able to absorb the energy from the surface. It's going to warm up. Atmosphere is going to warm up because of this long wave energy coming from the surface, and it reaches a temperature of Te. And this atmosphere is going to emit energy to space as sigma Te to the 4th, and it's also going to reflect the energy back to the surface as sigma T to the 4th, because if you have a warm plate you are holding like this, it's going to give you warm temperature on this side as well as on this side. So the atmosphere that is sitting on top of the surface is going to send energy back to space for energy balance, but it's also going to send energy back to the surface at sigma T to the 4th because a black body is going to emit the same energy in every direction. This is critical, very simple concept, but you should make sure that you understand it. So we won't add more to it, but you can go back to the equation we looked at and change the 4 pi r squared sigma T to the 4th by looking at the unit area instead of this average over the whole globe, and make the energy balance for the surface. So surface has S over 4 times 1 minus A coming in, and it has sigma Ts to the 4th going out, but also sigma T to the 4th coming in. Okay, so you have two energy sources for the surface. One is the long wave reflected from the atmosphere, one is the short wave coming from the sun. The best message to remember here is that the net effect of greenhouse gases in the atmosphere is that the Earth is warmer at the surface than it would be without a greenhouse blanket. So literally imagine yourself in a blanket. You are warmer because of the blanket. So greenhouse effect increases the surface temperature. This is the important message to remember. That's why we worry about increasing greenhouse gases, because the surface is going to get warmer. If the surface gets warmer, its long wave energy is going to increase, which will make the atmosphere warmer. Atmosphere has low heat capacity, but nonetheless warmer temperatures keep getting warmer is not a good thing. It will hold more moisture. It'll start to make many other problems like stronger hurricanes, glaciers melting, heavy rainfall, and so on and so forth. We'll look at that a little bit later on. So with that simple energy balance concept in mind, let's look at what the ocean is doing. Okay, so what should the ocean be doing? Ocean has high latitudes where there is more heat is being lost than is gained. Why? Because if you remember now the sphere again, and less energy from the sun being received per unit area, you begin to grow snow and ice, which is more reflective, so albedo is higher. So ice has higher albedo, and the sun's energy is coming at a lower angle at higher latitudes, which makes reflectivity be more effective. Low latitudes, they are receiving more energy per unit area, and the incidence angle is higher, so the ocean is able to absorb more energy because the albedo is lower at a higher solar angle, and that means more energy is being absorbed at lower latitude. What is the net effect? If you look again at this zonal mean meridional section, average all the longitudes to make the zonal mean. Zonal direction is the longitudinal direction, and meridional direction is the latitudinal direction. So you average over all longitudes and look at the meridional section to make it clearer, and you see that the energy shown in calories per square centimeter per minute, how much energy is being received every minute at every latitude on Earth in calories per square centimeter, you will see that the latitudes below about 35 or so is positive, which means more sun's energy is coming in than long wave being sent to space, more energy short wave being received than long wave being lost to space. As opposed to higher latitudes beyond those critical latitudes where the energy goes to zero because the long wave and short wave are equal, then you have at higher latitudes more long wave energy being lost and albedo losing more of the short wave, and lower angles of solar energy making less energy per unit area, and so on. The net effect is you are having a net loss of heat beyond a certain latitude in both hemispheres. There is some asymmetry here. This asymmetry is something you have to keep on remembering because there is more land in the northern hemisphere, there is less land. If you take South America, parts of Africa, Australia, and so on, you have much less land, more ocean. Antarctica is a continent with a lot of glaciers, so you have very asymmetric temperature distributions, energy distributions, and so on. Nonetheless, the critical thing to remember here, there are regions on the planet where there is a net energy gain. There are regions on the planet where there is a net energy loss. What does this mean? Obviously, it will have lots of consequences if you are constantly receiving energy more than what you are losing, and there are regions where you are losing more energy than you are receiving, right? The regions that are receiving more energy, more net energy, should get warmer and warmer, and the regions that are constantly losing more energy than they are receiving should get colder and colder. Does that happen? No. Why? That's the key thing about energy balance.